So hello and welcome back. So in this video we're doing another example taken from the Khan Academy. So the question is, after a certain medicine is ingested, the number of harmful bacteria remaining in the body declines rapidly. So it's about some number declining. The relationship between the elapsed time t in minutes, so t is time t in minutes, since the medicine is ingested, and the number of harmful bacteria remaining in the body, h of minute of t. So here you have minutes, and here your function is h of minute of t, is modeled by the following function. So h of minute of t is equal to 500 million times 0.2 raised to the power t. So every minute your function is the output of the function. As you increment t, another factor of 0.2 is being multiplied by your function, which means you are losing 80% and 20% remaining, and again of that 20% remaining, again losing 80% of that, 20% of that remaining, and so on and so forth, and it keeps declining just like that. So every second, so the question is about second, and here we had minutes. The number of harmful bacteria remaining in the body decays by a factor of what? So the question was, my function was basically h of minute of t, which is equal to 500 million times 0.2 raised to the power t. And now, so this function as an input takes t in minutes and then gives me some output. In order to answer this question, I need a function that takes a t in seconds, because based on this function I cannot know what's happening every second. So I need another function constructed based on this function to give me information, let's say every second. So in order to do that, I construct another function h of second of t, and I don't have to make any changes to these numbers. So 500 million is the initial point of the initial value of the function, times 0.2, and then here it's still the same function as I had over here, right? So if I enter 1 here as my input, so it becomes basically 1 second, because my input here is in seconds. So if I input 1 here into the function, it becomes basically 1 second, which is 1/60th of a minute. So t divided by 6, if I write it as t divided by 60, then when I enter 1 here, it goes into this function and becomes, of course it is in seconds, so then it becomes 1/60th of a, let me see, is, of course 1 minute is 60 seconds, so that makes sense. And so basically when I enter 1 second here, it goes into this function, becomes 1/60th of a minute. It goes into this function and becomes 1/60th of a minute. And so it's, in effect, it's basically the same function. The new function just takes I mean, when I have the new function, I don't have to do this calculation of 1/60th of a minute, or 2/60th of a minute, or 5/60th of a minute. It just does the conversion for me. So then, now if I enter here 60 seconds, let's say we have 60 seconds, so it becomes h of second of 60, and 60 goes here, it becomes 60 divided by 60. So 60 divided by 60 is just 1, and basically 60 seconds is 1 minute. And so it's again the same thing as inputting 1 into this function, and it gives me the same output. So, but now there is a problem here. The problem is that now based on this function, now I want to know every second, which is basically this function over here, the number of harmful bacteria remaining in the body decays by a factor of what? So this factor, as you can see, is not the right factor to consider here, because every time I make an increment, every time I increment t here, it becomes 0.2 raised to the power t by 60. So it's not, so basically I need to have only t as the index. Otherwise, for example, you change t from 1 to 2, but but the index itself has not actually changed from 1 to 2. The index has gone from 1/60th to 2/60th. And it's asking about every second. So when it's every second, then again I have to make sure that basically what happens here, and so it's just not. Let me tell you what I mean by this. So about this function, let's call it 2, and let's call this function 1. So in function 1, I have t, which is in minutes, and then I have h of minute of t. And so when my t is equal to 0, my output becomes 500 million. When my output becomes 1, it is the same 500 million times 1 factor of 0.2. When it is 2, it is the same 500 million times 0.2 times another 0.2. So you can see that with every time I'm incrementing t here, I know that the output of the function is being multiplied by a factor of 0.2. But this is not the case here in this function, because well, let's say in this function number 2, what happens is that, let's say I have another table. This is t, and this is h of second of t, and when my input is 0, my output is 500 million. And so when my input goes to 1, for example, then it becomes 500 million times 0.2 raised to the power 1 divided by 60. So it's basically the 60th root of 0.2. Now, what is the 60th root of 0.2? So the 60th root of 0.2, which is something around 0.97. So this is something about 0.97. So now, in effect, the output of the function has been multiplied by a 0.97, right? Now, if I make my input 2 here, it becomes 500 million times 0.2 raised to the power 2 by 60. So it's 0.2 raised to the power 2 by 60. So what is 0.2 raised to the power 2 by 60? It is the 60th root of 0.2 whole squared. And that is the 60th root of 0.2 whole squared. 0.2 whole squared, which is 0.95, something around 0.95. So you can see that this common ratio of the function, there is no way to know what's happening in the function every time I'm incrementing my input. So when I incremented my input here from 0 to 1, the number that was multiplied by the output of the function was 0.97. Then when I went from 1 to 2, the common ratio, or basically the factor multiplied by the output is 0.95, and so on and so on. So there is no way to know what's happening in the function this way. So in order to know that, what you can do is you can take this function number 2, which is 500 million times 0.2 raised to the power t by 60, and write this as 500 million times 0.2, or actually let me do this. Let me do something else. So you have 0.2 raised to the power t by 60. So you can write this as 0.2 raised to the power t times 1 by 60. And then you can rewrite this as, so basically you know that a times a raised to the power b times c is equal to, can be written as, for example, a times a raised to the power c, for example, whole raised to the power b. You can do that. So I'm using this here, and this is your a, this is your b, this is your c, right here, like this expression here, and I want to write this like this expression on the right side. So I can write this as 0.2 raised to the power 1 by 60 whole raised to the power t. So 0.2, so that is basically the 60th root of 0.2. So the 60th root of 0.2, which is 0.97, rounded off to 2 decimal places. 0.97 approximately. So now let me calculate what is 0.2 raised to the power 1 by 60, if I was not wrong there, which is the same number, which is right. So now instead of so that this becomes raised to the power t, of course. So now instead of this whole expression, I can write 0.97 raised to the power t. So what I'm going to do here now is erase this, and then I can rewrite this function as 500 million times 0.97 raised to the power t. And so now this becomes your common ratio. Every time you increment t here, one factor of 0.97 is being multiplied by the output of your function. And because it's a number less than 1, that means that your function is decreasing. Basically 3% decrease, 3% decrease in the output of the function. So then this becomes 0.97. That means every second here, the number of harmful bacteria remaining in the body decays by a factor of 0.97. That's how you solve this problem. Thank you.